Good morning, Panthers. Video number 2. We are going to talk about estimating delta H using bond enthalpies. Remember, delta H was a concept that we introduced in chapter 6. The way we calculated delta H's back in chapter 6 was we did calorimetry experiments. Burned Doritos in a calorimeter, measured how much heat was released, and using stoichiometry and a bunch of calculations involving Q and the heat capacity and all that other stuff, we were able to figure out the estimate, we were able to figure out the enthalpy of chemical reactions. That's a pretty tedious process. Experimentally, it's a pretty tedious process, and the math is a little bit tricky, and you got to remember all kinds of stuff about which way the heat's flowing. Is it flowing in or is it flowing out? So I know historically students have had a hard time just conceptually as well as mathematically with chapter 6 concepts. So here's an easier way to estimate the bond enthalpy. Now I want to emphasize the word estimate because we don't actually get an exact number. Like if you do the delta H calculation correctly using calorimetry, you're actually nailing down delta H of a reaction. This is a way to estimate how much energy it will take and whether a reaction is going to be endothermic or exothermic. So this illustration, this figure from your book, shows you what's going on. So let's say we start with some reactants over here. In this case, it's CH4 and chlorine. And we're going to react those guys together to form products of CH3Cl plus HCl. All right, so let me write down the chemical reaction for this that's depicted here. CH4 gas plus Cl2 gas yields CH3Cl plus HCl. I should note that that's a gas. And we don't know what delta H for this reaction is. Okay? So the way we can use bond energies to estimate this is we can take these chemical bonds that are in the molecule, these covalent bonds that exist here, and we can recognize, hey, if we break this whole molecule apart into its constituents, and then we go up the ladder, the enthalpy ladder, if we break the whole thing apart and then reassemble them the way we want to reassemble them, we can estimate the delta H. And how do we do that? Well, we already said in the last video that it always takes energy to break bonds. Whenever you break a chemical bond, it takes energy. So that's going to go on the plus side. In other words, that's going to move up the ladder. And then when we form bonds, it's going to be a negative number. It's going to go back down the ladder. And then we reconstruct whatever the molecule is we're trying to form. If we calculate those energies, the resulting difference between them will be our enthalpy of reaction, will be our delta H reaction. Okay? In this particular case, this reaction is endothermic because we end up with the products are at a lower delta H value than the reactants, therefore delta H must be a negative value. We also could have the case where the reactants or products ended up higher, let's say something like up here. In that case, delta H would be a positive number, and then we would have an endothermic process. All right, but for this particular reaction, it's not positive, it's negative. All right, so how do we do this? Let's take a concrete problem as an example. All right? So here is a problem for us that we're going to work on. So we want to estimate the enthalpy of reaction using bond energies and compare this to the standard enthalpy of reaction, delta HF standard equals minus 137 kilojoules per mole. So this guy right here, that is from the chapter 6 calculation. So that's if you go and you look up all the delta H's in a table and you were to calculate this reaction, you'd end up with minus 137 kilojoules per mole. The reaction is between hydrogen and ethylene. So this is something like the following chemical reaction. H2 gas plus C2H4 gas yields C2H6 gas. All right, and basically what's happening is this hydrogen molecule is inserting itself between the double bond. It's breaking that double bond, forming a single bond, and we're ending up with a new molecule that has one hydrogen attached to each carbon and then a single carbon-carbon bond in the middle, up in the middle here. Okay? That's the general idea behind the chemical reaction. Now, the key to recognize is, and the key to understanding why is it in this chapter, you need the Lewis structures. Why do you need the Lewis structures? If you want to pause the video for a second to think about that, and then come back, we can answer that question. And look at the question. Delta H sub F was minus. All right, so I'm gonna rewrite this reaction that we just had. H2 gas plus C2H4 gas yields C2H6 gas. And I'm also going to rewrite the Lewis structures. There's H2 plus C2, Lewis structures. Double bond between the carbons. Hydrogen surrounding the carbons yields C2H6. Hydrogens all around. Okay? So how do we tackle this problem? Well, we need our table of bond energies, just like we had before. And we need to, the way to do this is to realize that when I break these chemical bonds, breaking this guy, there's actually two ways you can do it. You can do it kind of a shorthanded way, which is figuring out which bonds are being formed. Like this is forming one carbon-hydrogen, a carbon-hydrogen, and breaking this guy apart, a carbon-carbon single bond. That's just kind of a shortcut way. I'm going to show you the long way to do it, which you don't have to, like, in your mind be visualizing how this thing reforms. So I'm going to make a table, and I'm going to call it bonds broken. Actually, let's do it that way. Let's do this in black. So we're going to do bonds broken on one side, and we're going to do bonds formed on the other side of the table. All right, so I'm going to look on the reactant side of the reaction, and we're going to say, all right, there's a hydrogen-hydrogen bond that's broken. There's carbon-hydrogen bonds that are broken, and there is a carbon-carbon double bond that's broken. So I'm going to show you where those are. There's the hydrogen-hydrogen bond, there's carbon-hydrogen bonds, and there's the carbon-carbon double bond. So I want to take accounting of these, and I'm going to say, how many of these bonds are broken? I've got one hydrogen-hydrogen bond, I've got 4 carbon-carbon bonds, and I've got 1 carbon-carbon double bond. Then the next thing I need to do is I need to look at the energy per bond. So this is where I go up to the table. I say, all right, it's a hydrogen-hydrogen single bond. That's right here. So that is going to be 436 kilojoules per mole. Carbon-hydrogen bond is 414 kilojoules per mole, and carbon-carbon double bond is 611 kilojoules per mole. And then what I just do is I multiply these guys together, because this is going to tell me the total energy for each of these bonds. So 1 times 436, that's 436. Carbon-hydrogen single bond, 4 times 414 is 1656. And carbon double bond, 1 times 611 is 611. And then what we need to do is we need to add these guys together, and they are 2703 kilojoules. That's the sum total of all those three things. Now, here's the key. It is plus 2703 kilojoules. Why is it plus 2703 kilojoules? The reason why it's plus is I broke all those bonds. Remember, breaking bonds always takes energy. So now I do the same analysis on the product side, and I say, aha, there's a carbon-carbon single bonds that are being formed, and there's a carbon-carbon a carbon-carbon single bond and carbon-hydrogen single bonds are being formed. So my bond types on this side are hydrogen-hydrogen, hydrogen-carbon, and carbon-carbon single bonds. I've got one carbon-carbon single bond, and I have 6 carbon-hydrogen single bonds, and then I'm going to multiply this times the carbon-hydrogen bond, which is 414 kilojoules per mole. The carbon-carbon single bond is 347 kilojoules per mole. If you're wondering where I'm getting them from, I'm getting it from this table right here. And so I'm going to multiply those guys together. 414 times 6 is 2484. And 1 times 347 is obviously 347. Add those guys together. That comes out to 2831 kilojoules. All right, now I'm forming all these bonds. Remember, you get energy back when you make bonds. It takes energy to break bonds. So this is going to be a negative sign out in front here. Negative 2831 is produced when you form these bonds. So using this information, I can now estimate delta H of reaction. So that's going to be equal to plus 2703 kilojoules minus 2831 kilojoules. And that turns out to be negative 128 kilojoules. In this case, it's actually per mole because it's a 1 out in front here. All right, so that's delta H reaction for this, negative 128 kilojoules per mole. All right, so it's an exothermic process. That's what the negative 128 means. Let's take a look at the prior page for a second, 137. So change color here. Delta H sub F is equal to minus 137 kilojoules per mole. So you might be asking yourself, why are these not exactly the same? Well, the reason why they're not exactly the same is the second one, this guy right here, this was done using like a calorimetry type experiment. You know those are tedious, you know they're difficult to do, but you also know you're going to get really good numbers if you do them carefully. So if you actually need to know the value really carefully, this is the number that you need. The enthalpy of formation of this molecule. But you don't always need to know exactly what the number is. You just want to be within a couple percent of the correct number. Well, if you want to be within a couple percent of the correct number, you can use this nice estimate we just did, which just involves bond energy. So as long as you know how to write Lewis structures, and you can take this table, you can estimate what the bond energy is going to be just by breaking the bonds and forming bonds and then creating a table like this. All right, in these sample problems, I have given you 2 sample problems you can try, and there's an answer, and you can see if you get the correct answer using the numbers from our table in this book. All right, thanks.